as I just said, this kind of screw or edge dislocation sometimes is created by some temperature, high temperature process. So remember that we introduced the low-cost process. In the low-cost process, we will deposit silicon nitride layer, and this silicon nitride layer will suffer from large tensile stress. Okay, and especially when we increase the temperatures, and this will create dislocations in your silicon material underneath. Okay. And either in your wafer process will have temperature gradient, or in your crystal growth, during your crystal growth process, will have temperature gradient. And this temperature gradient will also cause your dislocation. Okay, and for example, this the formal case, which means this crystal growth case, there's a different temperature inside and outside the seed. Remember that we put a seed in the melting silicon, and we can pull it out and become to solidify and change from liquid to solid. Okay, and like in your wafer process, when we try to heat up the silicon substrates, if we didn't heat up the wafers uniformly, which means that across the wafer you will have some temperature gradients among your wafers, then that will also introduce some stress. And this stress resulting from your temperature gradient can be given by this formula here. So you have the thermal coefficient, you have Young's modules, you have the temperature difference, delta T here. Okay. Okay, so now we'll move to the area defects. Okay, these area defects, we have staking force as our area defects, or grain boundaries, or and twin boundaries. Okay, and this staking force means you have some disturbance in your original regularities of your staking planes. For example, you have a plane like this, ABC3 planes, right? So the original arrangement is ABC and ABC, ABC, ABC. But you can see on the left hand and the right hand side here, as the arrow points out, we have A, B, C, and A, B, but C is missing. Now become like A, B, C. Okay, so we have a missing C planes here, which creates an intrinsic staking fault. Okay. And also here we have another edge dislocations forms accordingly. Or we have ABC, ABC, ABC. The arrangement like this, but now we have A, B, and it's supposed to be C. But between B and C, we have another A here. Okay, so this is also a staking fault, and we call it extrinsic staking fault, which you add another plane into your original arrangement. And again, you will form an edge dislocation, right, at the edge of this plane. Okay, so that's the staking fault. You disturb the original regularity of your planes. The planes can be either inserted or removed from the original lattice. So in the insertion case, we call it extrinsic case. In the removal, we call it intrinsic staking fault. Then sometimes if the staking fault is introduced by oxidation process, we call it OSIF, okay, OISF. And this oxidation-induced staking fault, for example, like in the low-cost process. Okay. Okay. Always from along 111 planes. Okay. Since you have more atoms density along your 111 planes, it's easier to observe this kind of staking fault. Okay. The density and size of staking fault, okay, we can measure it by chemical agent. Okay, because this chemical agent they prefer to attack those highly stressed areas. Okay, in those highly stressed areas, you have dislocations, you have a lot of boundaries or dangling tongues, so you have much faster reaction rates with your chemicals. So, well, you use this kind of chemical agent, you can see that similar as we just see that the surface piece is similar process that because those chemicals will attack some dislocation of defects first. Okay, and then now we move into the volume defects. Okay. Volume defects can be a void or precipitate or extrinsic or intrinsic point defect. So we can create a void or precipitate. Okay. And the reason that this dopant can precipitate is related to your solubility in your materials. Okay, it's also for the solid material, it also has a certain solubilities. Okay, we can imagine that we have done this experiment in the elementary school. You put a lot of salt into your water and you heat up, and you can dissolve a lot of salt. But when you cool down, then you see it become like supersaturated solution. So the salt can be easily precipitated when you cool down your temperatures. So similar as our solid material, okay, at high temperature you can put more dopants in your materials, and it become like supersaturated. When you lower the temperatures, then it begin to precipitate those excess impurity atoms. And those precipitate will create undesirable dislocations. Okay. And in silicon, like oxygen, okay, it forms like SiO2. Okay. Then you have some metallic impurities or dopants that will also precipitate. And but on the other hand, we can use these volume defects to help us to get more unwanted impurities. Okay, we will talk about this in our next chapters. It's also part of the cleaning process. Okay, this scattering process, because those defects, they tend to, or they prefer to get together. Right? So if you have this volume defect in your materials, it will draw or attract those heavy metals to those areas. So we can keep those impurities away from the surface channel, so which is good, and we call this scattering process. Okay, and we will introduce this process in more details in the next chapter. So this one defect, on the other hand, which is a good thing for us, can help us to gather more unwanted impurities. Okay. Now we will introduce like how we fabricate the silicon wafers. Okay. So the raw material, which means we use those coarse material, silicon oxides, because it's a natural form from our Earth. Right? Silicon will form become like native oxide, and we try to convert this coarse material into MGS material, which is metallurgic grade silicon. And this 中文就是叫做冶金啊，炼金术。这个在古代秦始皇就开始炼金的，这个就是在炼金的。但是这种 this kind of gray silicon still not very clean. Right? We wanted the purity like 99.9999, right? Like 5 or 6 9 or 7 9. We want a kind of purities for us to make the transistors. So in the beginning, we will try to transform the quartz SiO2 into silicon. So we can mix this quartz with carbon, like coal, coke. Like we can like burn it in the furnace and at very high temperatures. And this carbon will react with your silicon dioxide, and we have a melted silicon coming out. Okay, and then we take this MGS silicon and convert it to EGS, which means electronics grade. 就是做这些电子元件的这种等级。Okay, so we put this MGS powder combined with HCl, and that will produce silane, okay, or chlorosilane, or dichloro, trichloro, or tetrachloride. Okay, and we put this trichlorosilane in, or this kind of silane, then at room temperature they are in the liquid form. Okay, so we can further purify it by the distillation. Okay, we can like boil it and condense it back to a high purity liquid of silicon. Okay, this kind of process is we call it a chemical vapor deposition process. So we have this trichlorosilane, and we can put it with hydrogen and with some silicon rod. So those gases will react and deposit polysilicon on your silicon rod. Okay. And this polysilicon still has like 10 to 13 or 14 impurities. Okay. And this process is, we call it the Siemens process. Of course, it's invented by Siemens, the company. And then we take those polysilicon, we need to further purify it to get the single crystalline material for us. Okay, so now we will have CZ and FZ crystal growth methods. Okay, so first we introduce the CZ. Okay, so Krosky. I've been to Poland 2 times, but I still cannot pronounce very good Polish. Polish people told me that I think the Polish is probably one of the difficult languages to learn. Okay, we have like any students from Europe. Are you from Europe? Is that true? Polish?
It has a lot of different cases.
Yeah.
So you need to know which one to use.
Right. So where are you from?
Germany.
Germany? Okay. Danke. Okay. So we put those raw materials, okay, into this this crucible is made by graphite, and outside the graphite we have electrode. We can heat up the temperatures, so those polysilicon begin to melt, and then we can put a seed here. If we want like 100 plane, then we'll put 100 plane seed. Okay, and we dip into this melted silicon, and then we begin to pull this seed upward. Okay, so we put this seed upward. We can control the speed, because if you want the diameter smaller, you can pull faster. If you want your diameter larger, you can pull slower, and until you reach the certain diameter you want, then you can keep this constant pulling rate. Then you will put a whole ingot. Okay, and we will talk more about there's a physical model to describe this process, and the third part of these slides. Okay, and this pooled crystal is still contain oxygen and carbon, because this chamber, the whole chamber, you have a certain oxygen. And also the crucible is made by graphite, so naturally you introduce some carbon into your silicon. But like these oxygens, it can provide the mechanical strength. Okay, and also as I mentioned, there's a process called gathering process. Those oxygen form silicon dioxide and become the volume defect inside your bulk material that will help you to gather more unwanted some alkali metal. Okay, so nowadays, like all the wafers that we use, they come from this CZ method. Okay. So here's some pictures. So we dip this C and then begin to pull. Okay, so this is the pictures of this chamber. And there's another way to purify and to make the polycrystalline silicon into single crystalline silicon. This alternative process is called flow zone process, FZ. But the FZ basically is used for refining purpose in the beginning. So, for example, we have a polysilicon ingot here, and we have a coil. Then this IF coil can heat up this material. And So you can either move this coil, okay, you can move this coil. For example, here you will move it from the bottom and upward to the top of the ingot. So when your coil, when it get close to your silicon material, those high temperature will cause the silicon to melt. Okay, so only the region very close to this coil, the silicon will be in liquid form. Then we use a certain property. This property is that those defects tend to reside in your liquid form of silicon rather than in your solid. Okay, this different concentration or in your liquid or in your solid, we call this segregation. Because of this segregation process, we can move defect into your melted silicon. And as this coil continue to move upward, you can imagine that you draw all the impurities into this melted silicon. And once your coil move upward, here begin to solidify and turn into single crystal, and also more pure silicon can be formed. Okay. So in this case, we don't have like a carbon because we don't need to use a graphite crucible. Okay, and also can reduce the oxygen impurities. Okay. And I think we will talk about this segregation properties later. I'm not sure in this chapter or in the following chapters. Okay. 我用中文说一次好了，就是说这个 defect 它会倾向在液体，就是熔融态，胜过在这个固态里面。所以当你加热的时候，你的这个 defect 它就会倾向留在这个熔融的地方。所以当你在这个地方它开始凝固的时候 ，defect 就要说，哎，那我要在这边还是在这边？所以就跑到熔融的那个地方。好，所以它一路往上走的时候，它就把一些 defect 就一直带走。它就是一个在纯化的过程，然后下面这边呢，重新它在固化的时候，就变成是一个比较纯，而且是一个 CH3.Crystal 的这个 silicon。好，那这个 the defect of the we call it like a solubility in the liquid or in the solid. The ratio between this is the segregation coefficient. But I think we will talk about this later. Okay, so once we have this ingot ready, after we pull this crystal out, and we need to grind this rod to make it of the correct diameter or correct size we want. And also we will use tool to make a flash this ingot to help us to identify the crystal orientations. Like, for example, for N-type or P-type, we will have a different cut notations here. And okay, so once we have this ingot cut ready, then we can begin to cut it into different slices of silicon wafers. Okay. And then since the because we use those saw to cut these wafers, we have to polish it, to lap it to to a more flat surface. So we will use some CMP process to etching and polishing the surface, and then we can put a laser mark, to inspect or put a laser mark on it. So this is the wafer that we try to polish to make it like a mirror, and also we need to polish it to like certain thickness that because you for different process purpose, then you may specify like okay, I want 750 micron or that's the diameter. I'm saying about like 750. The thickness, okay, or like 1 millimeter thickness. Okay, so this lapping and etching at the same time, we call it like CMP, chemical mechanical polishing. Okay, so they can remove those damages and improve the flatness. Okay, so you can use this to make it rounded. Okay, your edge, and also you can polish it to make the flatness down to like 2 microns. Okay, so here is a table that describes that for different wafer size, for example, like 300 millimeter size, the thickness is around like 75 micron. And okay, and just for your reference. Okay, so here's another process flow that when you use the saw to saw your wafers, then there's a roughness on your surface, and after edge rounding and after lapping, then you create more flat roughness, and then you try to after your etching and CMP, you will create nearly flat, like mirror, virtually defect-free surface. Okay, then this is epi ready. We call it epi ready, means okay, you can use these wafers to grow the material on top of it. Okay. Okay. Now we get into the second part of the lectures. Okay, as I mentioned last time, right? Our lectures can be divided into 3 parts. Okay, the first one is to describe the properties. The second part, we will talk about some measurement methods, and the third part, we will talk about some physics or mathematic model behind the process. Okay, and in our homework, and we will need you to try to use those physical model, some parameters that we introduced that you can change in your TCAD software to simulate some process. Okay. Okay. So here we will introduce you 3 methods that we can that related to our wafers. Usually we try to know the resistance of your wafer, the resistivity. We try to know the type is P-type or N-type substrate. So here are 3 methods that we commonly use to measure our wafers. Okay, Okay, here the picture shown here is a hot probe method. We have two probes, and we have a voltage meter between these two probes, and we can heat up one of the probe. Like for example, we heat up this one, and once it is we heat up this probe, and we touch the wafers, this area, the temperature will be higher. So we know that if we increase the temperature, there's more, the covalent bond will be broken. So we will generate more free electrons and holes. So these free electrons and holes create like a higher concentration at this local area. So once we apply the voltage, or we apply the electrical field between these two probes, these carriers will move, right? For example, this is N-type silicon wafers, so that will generate more electrons. So if we apply positive and negative here, okay. No, sorry. That's another methods. Here, with these voltage meters, they don't apply. They just use to measure the voltage difference or measure the potential between these two probes. Again, so we have more electrons here, and it begin to like diffuse. Okay, diffuse to the other directions. So this electron movement or the diffusion of this electron will create potential difference in your material. Okay, so if you move the electron here, then here the potential become more positive, and here the potential become more negative. So if you use the voltage meter to measure, you can measure, okay, at the hot probe, you have a higher potential. And in this way, we can know that, okay, the substrate is N-type. Okay, so using this hot probe can help us to identify your conducting carriers. It's either electrons or holes. Okay. Like for example, if this is P-type, then you have a lot of hole in your hot probe here. So once this hole move to the cold probe, then now if you use the voltage meter to measure the potential difference, the cold probe will give you higher potential than the hot one. Okay, so in this case, you know, okay, now the conducting carriers are holes. So we know, okay, this is a P-type wafers. Okay. So that's the basic principle of the hot probe method. It can help you to determine either it's N-type or P-type semiconductor. And this diffusion current, okay, depends on this temperature gradient and also your mobility. Okay, so we can judging from the side of this voltage meter, and we know that what's the type of the substrate. And this effect, okay, since we use the temperature to generate more carriers and also generate the voltage or potential difference, this voltage we call it a seeback voltage. And this seeback effect is also another way that we can utilize it in our solar cell panel, right? Especially for the high voltage solar cell systems, because you use some optical lens or spherical mirror to concentrate your light into a certain spot. So it's not only increase the light intensity, you increase the temperature of the cells. So people can harvest the energy by this CPAC effect to generate some electricity for us. So this CPAC effect is often you can see this combined with your PV system. Okay, and then we try to not only the type, N-type or P-type substrate, we can determine. There's also very important for us to know the shear resistance. Okay, so how can we measure the resistivity of the wafers? Okay, this is the bulk resistivity that we can often to see this in some textbooks. So it depends on the mobility, depends on the electron and hole concentration. But in the semiconductor process or device area, we care more about shear resistance rather than bulk resistivity. So we define those shear resistance by this the following equation here. Okay, so we can write the bulk resistance in this formula, and the area we can use W and T. Okay, W is the area is the current that flows through this area, right? So we can use W and T to describe this area, and we can move the T, which is the thickness, W is the width, and T is the thickness. So this area is where the current will flow through, and we can move this T in front and combine this T with this law, and we can define this term as the shear resistance. So the shear resistance, if we define that this, you can see that usually the unit is, we can write it like ohm per square, or people write ohm per square. Just put a square here. So that's the unit of shear resistance. So we can draw this L and W on your mask. So we can draw certain pattern. So in this case, when we measure the resistance, we can infer the shear resistance of this material. Okay, so but remember, when we measure the resistivity, we have to remember that we have to we don't want to count the resistance of your probe. So if you just use two probes to measure these materials, the voltage you measure will be not just the I times the resistance of this material, but also your I will flow through this probe area, and your probe will contribute a certain amount of resistance in your measurement. So we need 4 probes to do this measurement. Okay, so for example, on these outer 2 probes, we can force the current, and this current will flow through to form a loop like this, and we use this inner 2 probe to measure the voltage difference. So we just measure the voltage difference, so we won't have current flow through these 2 probes. So we can just measure the difference here. So now the resistance will be this V divided by I that we forced here. Okay. So in this 4-probe method, the current is carried out through the 2 outer contacts, and the voltage drop is measured across the 2 inner contacts. And we have a constant Kp. This constant Kp depends on your configuration, your position, sometimes your thickness of your wafers. Okay, so for example, if we have a 4-probe configuration like this, the distance between 2 probes is S. Okay, there's a spacing. If that S is small compared to the dimension of the whole wafers, and is large compared to the layer thickness T. Okay, so this Kp can be reduced to this pi divided by your natural log 2. Okay, so there are a lot of papers a long time ago. They conducted many experiments to try to use different orientation or configuration, try to calculate the correct shear resistance. So I think in this case, it's very common. Like say, if you probe like 10 micron or 20 micron or 30 micron, and the layer that we are interested in, the thickness, for example, is only 1 micron or less than 1 micron. And the wafer size, okay, is pretty big. Okay, so now we can apply this formula directly. Okay, but if the configuration is different from this condition, then this number Kp will be changed. Okay, so again, there's a papers in the textbook as a reference. If you are interested, you can check it out. Okay, and the third very important measurement, we call it Hall effect measurement or Hall measurement. Okay, this Hall measurement is very powerful and is commonly used today to characterize the material that you grow. It's so powerful that it can provide the type, which means it's electron or Hall to conduct your current. It can also provide your carrier concentration during the measurement and also the mobility. Okay, so the Hall measurement is a very powerful technique to characterize your material. And you can, in this measurement, you have to apply some magnetic field, okay, to help you to get a correlation correctly. Okay. Let's see. Okay, so here, this is the 3D view of your material. Okay, so you have your T is the width, and W is the height here, and this is the X direction, and this is your Y directions, and this is your Z direction. Okay, so let's define this direction first. And the right-hand side of the figure is a top view. Top view of this. We will make like certain layout or certain pattern for us to conduct this experiment. Okay. So like we have like different terminals or different nodes for us to probe or to provide or to measure the voltage or current here. Okay, so we can, in the beginning, we can force a current Ix in these directions. Okay, so we can force the current Ix, and things, the current flows through this material, and it will create a voltage drop, like Vx between like certain distance, and this resistivity can be defined by these equations, that you have Vx divided by Ix, and W times T, and over S. S is the distance between these two. Okay, I think it's very trivial, right? Now, if we normalize this dou by T, then we can have the shear resistance. Okay, so now we apply a perpendicular magnetic field BZ, and this, okay, in this direction, Z direction, we have a BZ applied in this direction. Okay, and this magnetic field will create a magnetic force, and this force is related to your velocity here, and also the magnetic field. And if you write in the vector form of your F, V, and B, basically it's a cross product, right? Your V cross your B. But if we put it to the directions here, we can just write VD, your dream velocity, and your BZ, because Z is in your B is in your Z directions. Okay, so this Ix, since here we force that Ix will be equals to your concentration times your Q charge and times your area and times your velocity d here. So we can use Ix to represent V and plug it into these equations to replace Vd here. So now your this Lorentz force will be related to the current you apply, and also the magnetic field you applied. And this magnetic field, this magnetic force, under equilibrium condition, that will balance out with your electrical force, okay, to prevent your charge to build up. Okay, so now this magnetic field will be equal to your electrical field, and your electrical field is the current or the voltage you applied right here. Okay, so this electrical field we can use VH divided by W. Okay, the V so anyone wants to guess what's the direction of your FM? Does anyone know that? Your V is in your X direction. What is the direction when your X cross product with your Z? You have X, you have Z. So the third one will be Y, right? But is it positive Y or negative Y? Negative? Okay? Take out your right hand. X is in this direction, right? And Z is this direction. So this is the point out, downward negative y directions. And if you have charge, this magnetic field, will move your charge, try to move it to the bottom of this material, but that will cause the charge to build up here. So there has to be another force that to counter this effect, right? So that will be your electrical force. Okay. So this electrical force will be equals to your magnetic force. So we already have these two. Now you can rearrange this formula. So we have this whole voltage VH. We can measure this VH. Then we know the type and carrier concentration because IX and BZ and thickness Q. Those are you already know this number, right? Okay, so here's just another figures that you can see here. This is the X direction, and you have magnetic field this direction. So this create Fm point to your left hand side. So you have another Fe electrical field point to the right hand side to counter this to prevent the charge to build up. Okay. Now, so we can measure this voltage, or we can define another Hall coefficient called RH, which is related to your VH. Okay. So if you plug this RH into this equation and move this N or P to the other side, then we have these equations. So you have positive sign or negative sign represent your holes or electron respectively. Okay, so then we can combine these equations. So we can measure the resistivity and the mobility at the same time. Okay, this is the resistivity equations. So you have concentration, then okay, so we can get your mobility. Okay, this whole mobility is different from field effect mobility and situation mobility, and you may know already, or you can learn this from the semiconductor device physics course. Okay, so that's the whole measurement. I hope you can understand the explanation. And we also can do some physical measurement. Okay, so we can use some agent, right? The agent listed here. If you put your device or your material into this agent, they will create different edge patterns or edge profiles. Okay, so if you have a staking fold here, then you have dislocation here, you have some precipitate or point defect here. So once you dip your wafers into these edges, they will create different, like a circle, dash. Then you can judge from your surface tomography and all those profile. Then you can easily to identify. Okay, here we have like staking fold. Here we have dislocation, and here we have what. Okay, so these are some physical etching experiment that we can do. Okay, and we can also measure the impurities, but impurity is very difficult to measure. Sometimes you cannot, physically to observe your defects. So we use some more sensitive measurement, which involves some optics in here. Okay, this is called FTIR, Fourier transport infrared spectroscopy. Okay. So we have a IR source here, and here's a semi-transparent mirror, and you can prove the sample you want to measure here. And there are two arms. One, you have one mirror that's fixed, and the other arm, you have a mirror that can move, and you can control, use some piezo motors, electro piezo motor, and you can control like precisely the movement of your mirror. And you have the IR light source. Then when it goes to this semi-transparent mirror, you begin to split into two arms. The first one goes to here, and then reflected down to your sample. Okay, and the other one, again, half of the light will transparent to this, and when you reach this mirror, it will be reflected back to this mirror, and then go downward. So once you move this mirror periodically, right? Let's say periodically you move this mirror, then create different your light path, optical path for this second arm. So when you move to maybe right hand side, the light will travel a longer distance and then reflect it back into your sample. And you move to your left hand side, the light will travel a shorter distance. So this creates a phase shift between these two arms. So the light will arrive to your sample with different phase, right? So since this one is fixed, this mirror is fixed. So those two light with different phase shifts will construct like constructively interference or destructively interference around the sample here. Okay. So they will have different light. When it's interference constructively, then the light intensity is larger. Okay, so then you will create different absorption spectrum in your detector here. So we can detect those signals and do some signal processing. Then we can transform from the space domain into the frequency domain. Since you are moving this periodically, so let's say like a sine wave, right? So in your frequency domain, it looks like a certain wave number or certain wavelength or certain frequency. They all mean the same things. So here we just plot into the wave numbers. Okay. So you can see that from these spectrums, from this spectroscopy, you can identify the different absorption dip, and these absorption dips represent a different impurities, sometimes oxygen or carbon or some compound inside your silicon materials here. Okay, so that's we call it the FTIR. And we also can use some microscope, but not optical microscope. It's a scanning electron microscope or the transmission electron microscope to check the quality of your material. Okay? Because electron, they can have a more smaller wavelength compared to your optical wavelengths. So it can down to like 0.1 nanometers. So like for example, this is a TEM pictures. This is a silicon and this is amorphous silicon dioxide. So you can see there's an interface here. Okay, now let's take a break, then we'll come back in 5 minutes.